So today we will continue with the application of the class, and specifically we are going to discuss how to derive diffusion laws in dendritic spines. So I will explain what are dendritic spines, though there are microdomains located on the surface of a neurite, and what is the meaning of deriving, in a sense that how we can use the narrow escape theory that we have developed to find out the residence time of diffusing particle in such a domain. So let me go back and explain a bit of some neuroscience background. So of course, you know that the brain is made of neurons. We have neurons, and we have other populations such as glial cells. There are blood vessels, and all kinds of other structure. So neurons are basically made of a soma. We have here the soma of the cell, which connect. We have the dendrites, which collect informations, and so this is the soma. We have here the dendrite, and this is the axon. And specifically, we know that neurons connect at microjunctions here. So this is the soma, this is the axon of another neuron, and there is this particular junction here that will be of interest, which is called a synapse. And let me show you some picture of this, but maybe before, what is important is I shall remember these following experiments, that if you stick an electrode here to this neuron, and if you send here a spike, you have a stimulation. So this is a stimulating electrode where you do stimulation. And then if you record in that neuron, so this is the pipette, the recording electrode, then what you see in this recording electrode here, so let's call it 2, what you see in 2 is that as a function of time, this can generate a current. So this is the current here that can be generated. That is, when you stimulate electrode 1, when you stimulate 1 and you record in 2, at time 0, this is where you get the stimulation. And once this is done, what you see is that this is the current you get. So this must be induced by something that happened at the synapse. And interestingly, there is a protocol called long-term potentiation, LTP, long-term potentiation, by which you can modify the result of the induction, the result of the first electrode. That is, after LTP, when you repeat the protocol, so this is a protocol that I'm not discussing, so this is long-term potentiation. So after this is done, when you repeat the protocol, instead of having the currents that you have seen, you have now a current with a different amplitude, and this is stable. So this is after LTP. So why this introduction? Why saying that you can generate here a stable current? Because the mechanism by which this happened is still unclear, and it seems that the diffusion of molecules, ions such as calcium in spine microdomain is a key, the residence time of calcium in the spine is a key feature. So now the question we wanted to ask in terms of modeling and mathematical analysis is how to calculate such a diffusion time. So before entering into this question, let me show you examples of structure of dendritic spines. So this you can see from here. This is a picture of hippocampal neurons, where you can see a dendrite. And so if you magnify the region here, you see these beautiful figures where you see this protrusion. There are different shapes. Some looks like mushrooms, some looks like filament, and those are called these dendritic spines. You can see here there's another example where you have this protrusion, and in red here you can see where you have presynaptic terminal, where you have a connection to another neuron. So you have here an example of a beautiful spine with a head, with a long neck in here, that is and it connects with another neuron. So of course, when you have such a connection that is well established, this is what is called a synapse. And upon activation of the presynaptic terminal and release of neurotransmitter, you can have opening of the channels and entering of calcium, as you can see here. And the question we'll be interested in is, what is the residence time? How long calcium stays inside a spine? So we have to define this correctly. What is the meaning to stay inside this? It means, for example, if we have here an artificial boundary, we can say that this is the time that you have a Brownian particle that will hit this part here, and this is lost now inside the dendrite. And of course, why this is important, we have about hundreds, we can have up to hundreds of thousands of spine per neurons, and they are involved in defining what is called the synaptic weight. And today there's still a question of the debate about what the dendritic spine are good for. And I'm going to leave that as a question that is currently under debate in the literature, where people discuss the electrical properties, and there is also their biochemical properties. And today we are more discussing this biochemical property to explain how they regulate calcium dynamics. Let me show you some other figures. So you can appreciate the diversity of such a structure. Here you have the philopodia. Here you have other type of blob with mushroom type spine. In red here you have a structure which is called the postsynaptic density, PSD, postsynaptic density, which is not going to be important for our purpose of today. And this is a presynaptic neuron. This is presynaptic, this is postsynaptic neuron. So you can see here the cleft where particles are going to diffuse. And so diffusers are neurotransmitters that will diffuse here to open channels from where calcium will go in. And now this is the dendritic spine that we'll be interested in. And so we shall ask the question how to calculate the diffusion of a particle inside here such a structure. And how are we going to calculate this time? So first of all, why this is sufficient? So if we have such a structure, if you have a diffusion of a particle starting at position X, what we can show first is that the process can be characterized by one number, which is the mean first passage time, E tau, which is the mean first passage time, MFPT, from, let's say, the point X, which is here, to the absorbing boundary, d omega, which is at the border between the dendrite. So this is the border between the dendrite and the spine. And so, in principle, what you have to write to study this process is the probability density function for such a particle, which if it is just if it's a pure diffusion, that is x dot equals square root of 2d w dot. This is a stochastic equation. The probability density function just satisfies the classical diffusion equation. So this is a diffusion equation with the correct boundary condition, which is reflecting boundary condition dpdn here everywhere. So this is the reflecting boundary condition everywhere here, except at the absorbing part where we have absorption. And the general solution can be expanded using the eigenfunction and eigenvalue for such a domain, phi k. This is the eigenvalue and eigenfunction. So those are the eigenfunctions for this associated with this associated boundary condition. So the boundary condition are those defined here. And with this eigenfunction and eigenvalue, so this is a compact domain, so we know that the spectrum is discrete. You have the first one, the 0 one, the second one, and the spectrum goes to infinity. It's not clear how to calculate the spectrum, but the probability density function px of t is the sum of the exponentials of the lambda kt phi k of x, and there's a coefficient ck, which can be written c0 exponential minus lambda 0 t plus c1 exponential minus lambda 1 t. So we have seen that for the narrow escape problem, which is the case here, the first eigenvalue lambda 0 is very close to 0, and the time it takes to escape from such structure when you start at position x, which is inside the head, the time it takes goes to infinity. Let's say when the radius of the neck, let's call it little a, when little a, the radius of the neck, this is the neck radius, is small. And in that case, we can make the approximation. So the rest of the spectrum, lambda 1, is much larger than lambda 0, which is close to 0. So since when you are looking at the escape, since the time is long, much longer than the time it takes to equilibrate, what we get is that P can be well approximated by the first term lambda 0 t, and this we neglect the part here. So this is for a time t long enough, for example longer than 1 over lambda 1. So in that case, this process is Poissonian, and what is needed is really the first eigenvalue. And actually what we have seen from the narrow escape problem, that this lambda 0 is exactly 1 over the mean first passage time for a particle to escape. Thus, we just need to calculate this mean first passage time. This is MFPT. And this is the goal of today, to calculate this time. All right, so let's now formulate the question about this time and how to calculate it. So again, we start with the dendritic spine. of size L. This is the neck of radius A. This is the head with volume V head. And so we are interested in estimating the mean first passage time, which is the solution of a Laplacian u equal -1 in the spine, which is the domain omega, u equals 0 in the absorbing part, and du dn equals 0 everywhere else, with the diffusion coefficient d. And for this part of the calculation, I will assume that d equals 1. Later on, we will write the formula with the full d. All right, so to do this, let me remind you that if the length of the neck equals 0, the mean first passage time is nothing but that the narrow escape time, which we have seen is just the volume of the head divided by 4dA, plus other residual term. So this is the leading order term. This is the leading order. Note that it goes like 1 over A. So this is the expansion can be done in 1 over A. So now what happened when the length here of the neck is not 0? So for this, we are going first to study the equation inside the neck. So inside the neck, we still have d Laplacian u, which can be written, so let me say d equals 1, so this is just d du dz squared. So let's orientate this with the arrows. This is z, so this is size 0, this is the height L, capital L. So if we do a 1D approximation, then in this 1D approximation, the Laplacian becomes 1D, and this has to be equals to -1. So the solution of this equation is just u of z. We have to integrate twice, so this is minus z squared divided by 2 plus c1z plus c2. Now, due to the absorbing boundary condition, since u of 0 equals 0, we need to have c2 equals 0. Now, to calculate c1, what we will use is the compatibility condition. So, the compatibility condition, and this is obtained by integrating the equation over the entire spine domain omega, which is just summarized by this equation. This is du dn, and we have to integrate only over the absorbing boundary condition, ds. And since we use the 1D approximation, this is du dn, so this is the n, the outward normal here. So n is finally minus ddz. So this is simply u prime minus u prime z. So this is for z at position 0. So this is u prime 0. And the surface is just the surface of the cylinder, which is pi a squared. On the other hand, this is equal to -1, so this is equal to minus the volume of the head plus the volume of the neck. Right, so finally what we get for u prime 0, u prime 0 equals volume of the head plus volume of the neck divided by pi a squared. And this, by definition, this is just equals to c1. It's just what you get when you derive the expression for u of z, given in this is a star here. Right, so ultimately this says that u of z is given completely by minus z squared divided by 2 plus this term vh plus vn divided by pi a squared z, and that's it. And we will use this as a condition that we are going to impose on the connection here between, so let me take another color, between the spine head, this is the head, and the neck which is here. So let's keep this formula. We will come back to this for the next slide. So this is again minus z squared divided by 2, v head plus v neck divided by pi a squared z, and this is u of z. All right, so now let's continue. So we now need to calculate, to estimate the expression, the solution of the equation Laplacian u equal -1 in the head. And so for this, we are going to use what we developed for the narrow escape theory, which is Laplacian, the Green's function of the head only, which is Laplacian g equals minus delta Dirac, and the GDN equals -1 divided by the volume or the surface of the head. So I invite you to look at the class about narrow escape for this, our narrow escape class. And so when you multiply this by j and these by u, and we use the Green's identity, so Green's identity, we derived an equation for u of y. So u of y plus the integral of the Green's function jxy d volume of x over the head equals the so let's call this boundary between the head and the neck, let's call it d omega head neck, and this is the Green's function jxy du dn of x dsx plus a constant. And so what we are interested in is the mean first passage time, and we will see that actually what we need to calculate is the constant c. How to calculate c. So this needs to be calculated, to be computed. Okay, so as the size a goes to 0, we know that this is going to be of order 1 because this is independent of a. And so u will be characterized by the first term here and the constant c. So to calculate these two constants, we need two conditions that are coming from the continuity condition and the flux condition, the continuity of the derivative. So we will write the continuity condition here. So for example, the continuity condition for the mean first passage time is to say that u at, so again this is u at L, can be computed from the continuity with the 1D approximation, which give us minus L squared plus VH plus V nec divided by pi A squared L. On the other hand, this is equal to, so this is the Green's function for 2 point x and y, which are exactly, again, now I'm choosing a point y, which is at this intersection between the head and the neck, for which we have this, and du dn, this is the flux, plus the constant c. Now we need to estimate the flux here. Now we know that for a 3D hole, the flux has the shape E divided by A squared minus R squared. This is for a cylinder or a disk of radius A, and R here is this is the radius. So if we now write the condition for the flux, so if we integrate this equation, the first equation over the head, what do we get? We get that du dn, which is minus 1, so this is equal minus the volume of the head. This has to be equal to the integral of du dn over the d omega of head neck intersection ds. So since we are looking for the orthonormal, so this is going to be minus E integral from 0 to A of E A squared minus R squared, and now we have to integrate 2 pi R dr. Right, so there is no need for A here, this is outside, so this is equal to what? This is equal to minus E, and now this integral can be calculated easily by changing R equals AU. So in that case we get A squared, right, A squared divided by A, and we have to integrate this, so this is 1 minus R squared, and there is a square root which has to be integrated between 0 and 1, and we are left with 2 pi. So finally this is equal to minus A 2 pi, and at 1 this is 0, so that's it, and this is equal to minus the volume of the head. So this gives us exactly the value for E that we need, and that's the flux. Now we have to plug this into 1 and to calculate, so let me write it again, minus omega h equals E minus E A 2 pi. Now we need to calculate, so let's do that in the next slide. Let's calculate the this term here. So I will rewrite it. So we need to calculate the integral of jxy du dn ds over the intersection between the head and the neck, and this can be written, so for x again, so we are exactly at the intersection here, so this is L, this is the length L, so the Green's function can be written, so the leading, we're just going to take the leading order term, which is in dimension 3, 2 pi and not 4 pi, 2 pi 1 over R. So let's take a point here. Let's take the point y at 0, and x varies inside here the disk, for the connecting disk. du dn, this is e divided by a squared minus r squared, and now we have to integrate with the minus, because this is the outward normal, so the normal is in that direction. And so this is this integration from 0 to a dr, and we have to multiply by the surface element. So this and this goes away, and we are left with minus e integration from 0 to a of dr divided by a squared minus r squared, which is again, by changing variable, is equal to integral from 0 to 1 of du divided by 1 minus u squared, which is exactly arc sine of 1 minus e, and arc sine minus 1, this is exactly minus e pi over 2. So now we are ready to collect all the information from the previous, so we know what is e. E is exactly, so this is from the previous page, e is exactly volume of the head divided by 2 pi a. So on the one hand we had minus L squared divided by 2 plus volume of the head plus volume plus the volume of the neck divided by pi a squared L equals to minus the volume of the head divided by 2 pi a, and there was the other term that I said there was of order 1, plus the c term that we didn't know that we were looking exactly for its value, right? So let's go back. Let's check that this is what we had before. So this is the formula that I'm now using. I think we are correct. So let's continue. So if now we continue the calculation, then what we are left with is that we have minus L squared divided by 2. So the volume of the neck is exactly pi a squared multiplied by L, right? So volume of the neck is pi a squared multiplied by L. So let's write it, volume of the head divided by pi a squared L, and this is give us now the term L squared. And now let's move this term to the other side, so we have VH divided by 2 pi a. 2 pi a, and I think we forgot here to multiply by pi over 2, which is coming from here. So this has to be multiplied here by pi over 2. So pi and pi goes away, and we're left with VH 4a, and this is equal to the constant c. So finally we get that VH divided by pi a squared L plus V head divided by 4a plus L squared divided by 2 is this constant, which is actually the mean first passage time for a particle that starts far away from the boundary. That is, for any particle that starts, let's write it in green, in red. If you start away from here, for any point starting at point x in here, the mean first passage time, as we've seen from the narrow escape theory, is about constant, and it is equal to c. And so now if we have a diffusion constant which is not equals to 1, we have to divide everything by d. And this is the mean first passage time it takes to escape from the spine head. So it's remarkable that in the narrow escape, the escape rate was 1 over a. Here it's like 1 over a squared. So this formula said that the time it takes to escape has to do, you see, suppose that when a particle arrived here at the intersection, there is a mechanism that prevents it to go back to the head. Then the time would be the time to escape here. This is the t narrow escape time, plus the time it takes to escape from a cylinder, which is L squared divided by 2d, which is the sum of these two terms here. This says that the first term here has to do with the recursion. That is, all the particles that ultimately, once they are entering into the head, they go back into the head, and this can be done an infinite number of times. And this has been shown in the paper with Armin Bis in Physical Review E in 2007, which I invite you to have a look if you want to see the detail of the simulations. And there are other consequences for this formula. First of all, this is a formula about diffusion. That is, how long it takes for particles such as calcium to escape from a dendritic spine. So it has nothing to do with electrodiffusion, and in particular it has nothing to do with any type of resistance of the neck. It has to do with diffusion. So this is an important point, because this is not what has been discussed in the literature. Especially I refer you to the paper of Svoboda in Science in 1996. So to conclude, I would like to say that we've seen here that using diffusion property and using specifically the geometry of a dendritic spine, then you can calculate this time, the residence time of ions. And this residence time is exactly the reciprocal of the rate when you approximate this process, let's say by an exponential. We recently looked at an extension of this, in particular when instead of having a non-smooth connection here, you could have a smooth connection, and then the shape of the connection here is like a cusp. So this connection can be approximated as a cusp. And interestingly, instead of having a leading order term that will be affected, the leading order term stays omega L a squared, but the next term is changed. For example, if we have a cusp, there is a constant here, and it is divided by a to the power 3/2 instead of just 1 over a plus other terms. So this is in the paper with, so this is Holcman 2011 in Journal of Mathematical Biology, Mathematical Neuroscience. Okay, so to conclude, we have seen here an application of the Narescape formula to calculate the residence time of calcium inside structures such as dendritic spine, which reveals how it depends on the geometry of the structure.